Hello and welcome back. In this video we'll begin with a question. Why visualize data at all? Looking at numbers should be sufficient, right? Well, here's an example. Now this is stock prices from a national newspaper, and even if it was high resolution and your eyes were good enough to read it here, it's going to be hard to know what's going on. Is it a good day for the markets as a whole or a bad day? How is the particular stock that you're interested in compared to others, etc. It's going to be difficult to make any sense of these sorts of numbers. Now, it turns out it's a bad day, and this is a pretty effective way to hide your data in these sorts of tables. This is not how we want to analyze our data. So that's an extreme example, of course. So let's look at the other extreme. Let's look at a teeny tiny data set here with only 15 rows in it, or observations on two columns or variables that we call x and y here. Now, remember in bioinformatics we'll often have thousands and thousands of data points that we're analyzing. So this should be easy, right? We're all smart, and if you stared at this for long enough, you should be able to find some sorts of trends or patterns, right? Now it is going to take you, and it's going to take me, some time and effort to stare at this and figure something out, even for this small data set here. Now, you might be motivated, and this would be a good motivation to have, to calculate some summary statistics to help us out here. That's a sensible thing to do. And it does indeed help to some extent in this case. For example, here we see that the data falls between similar sorts of minimum and maximum values, bounded between here, this -5 and +5 in this case. The mean or our average here is also rather similar, and it's quite close to 0 in this case. And indeed the other values here are rather similar too. So we have learned something about the data. However, if you just plotted the damn thing, right, you're going to engage your visual system, this highly efficient data conduit, right into your brain, and you'll see the relationship between these variables super quickly, right? In a fraction of a moment, we'll see that they all lie on the surface of a circumference, the surface of a circle here, the circumference of a circle, in other words, right? Our visual system is great at seeing these sorts of patterns, so why not use it? Now, a side note here is that we might have picked a different way to plot the data. For example, we might have made a plot like this first, where rather than x versus y as we had in our last plot there, we've maybe plotted x and y separately versus their row number. Now this would be common, for example, in like time series data, where our data points are collected at different times, and then the bottom axis here would be time. Now this is of course not maybe as effective as a visualization as the previous plot that we showed, but it is still better, I'm going to argue, than showing. It's better at showing how the data fluctuates, and we learn certainly a lot more about the data and the trends in the data than staring at that original table of numbers for long periods of time. Now, the point here really is, if we go back to that previous visualization, that we'll often want to try out and explore different types of plots, different types of visualizations, iteratively and pretty quickly to learn about our data. And we want to kind of cultivate this mindset and have a system and tools in place at our fingertips, right, where we can do this quickly and easily. Now, because what we're doing here is a kind of necessary first step in any data analysis workflow, that is exploring our data, the take home here is that we should always kind of look at our data if we can. To put it another way, if you can't see it, then don't be too quick to believe it. So what exploratory data analysis does, this EDA approach, is it allows us to visualize distributions and relationships in an effective, quick way. You can then detect errors, which is, of course, vitally important for quality control purposes. If we have crap data coming in, we're going to get crap answers coming out, regardless of how fancy our bioinformatics analysis pipeline is, for example. We need to assess where the data what the data is like. Is it going to be suitable for the type of analysis we want to proceed with, for example? And this EDA approach, it really focuses on what can the data tell us, rather than, for example, testing some predefined hypothesis that we might have had from the outset. In short, EDA, or exploratory data analysis, provides us with a set of techniques for visualizing and summarizing data. This approach, this EDA approach, and indeed the terminology, was really championed by a number of researchers at Bell Labs in the 1960s, who were really like the Google of their day. In particular, John Tukey, shown here, who also developed the fast Fourier transform algorithm and coined the term bit, amongst other major developments in the field. He introduced and promoted many fundamental EDA techniques summarized in this book here behind me, including things like 5-number summaries. That's like the min, the max, the median, and all those quartiles that can summarize the data distributions, box plots and stem and leaf diagrams that we'll see more about in a moment, and a number of other techniques. These techniques, critically, they're more robust to skewed and long-tailed distributions that we often have in real-world datasets, which makes them so useful for our purposes. So these sorts of exploratory data analysis techniques should really be the first step of virtually every new data analysis project that we'll encounter. So how do we go about it? How do we start summarizing data? Well, let's open up RStudio, please, and do that with me. Pause now and get RStudio open up. And then in your console, please enter in this code to make a little vector called x with 1,000 points randomly taken from a normal distribution. That's what this rnorm function does here. You can and should check out the help page here of the norm function to find out more about how it works. Once you've done that, you can calculate some standard summary statistics that are fine for normally distributed data, such as the mean and the standard deviation as shown here. We can also calculate so-called summary statistics with the summary function. This will give us the minimum, the first quartile, the second quartile, also known as the median, of course, the third quartile, and the maximum values from our distribution of data. Now, a popular graphical summary of those summary statistics introduced by Tukey and others is the boxplot, the so-called boxplot shown here. What this shows is the interquartile range between the second and the fourth quartiles. That's that little rectangle or box. The median, that's the line across the box here, and the range of the data is shown as the line extending from the box, what some people call the whisker. If you call this a box and whisker plot, that extends here from that box region. Now, another popular and probably more intuitive visualization for a distribution of data is the classic histogram. And this has been used for a long time. Many people are familiar with this. The basic idea is that it's based on binning of our data into equal width bins and then drawing rectangles for each bin with the heights of those rectangles corresponding to the data counts within a particular bin. Now you get to decide the widths of the bin, of course, right? There's a default value here like we've just used that's determined on the fly for us, but you can and you usually should change this bin value as we'll see in a later video and discuss at some length. Now, a good strategy here, a good compromise, again, is to show the data. And we can do this by adding little what were called tick marks here with this rug function at the bottom marginal region of the plot here. These little ticks, they lie where the data lies. And the reason it's called the rug, of course, is it's meant to look like the tassels of one of those fancy floor rugs you might find in some people's homes, right? These are the rugs or the ticks. So we can do that here with the rug function for base R plots like this one. We're going to see how to make these sorts of figures not just in base R, but also add-on packages like ggplot and others in our next video. So this show me the data issue that we'll often come back to, it's very well demonstrated when we have data like this. This is taken from Anscombe's classic 1973 demonstration of the trouble of relying solely on summary statistics and then going off and doing your routine analysis. So what we have here is 4 small data sets from Anscombe, and we've calculated some classic summary statistics like the mean, here the standard deviation and the R-squared, etc. from a linear regression fit. And they're all the same here for each of these data sets, suggesting that these are rather similar. However, it's not until you just plot them that you realize they are indeed very different, as shown here in these figures from Anscombe himself. And you can read more about this data set and some of the statistics from them at this Wikipedia link here at the bottom where I obtained these figures from. Now, an even more surprising example perhaps is shown here, plotted in R. Each one of these data sets that's shown coming up here behind me has the exact same summary statistics to 2 decimal places. Again, just like those Anscombe's quartet data that we saw in the last slide. But yet they're clearly very different when you plot them. So there's no summary statistics around that I know of that'll show you have a dinosaur hidden in your data, ready to roar at you and cause complications later on. So the take-home point here is that we really want a kind of working mindset and an environment at our fingertips where we can plot and visualize data quickly and iteratively to explore it and analyze it, just like this. Now, this is exactly what R gives us, and it's why in the next videos in this section we're going to learn how to make these types of compelling figures in the R environment. I'll finish this video by just highlighting a couple of resources to take you further with EDA, this field of exploratory data analysis. These include the free RStudio Primer in this first link here. This is an excellent resource, and everyone should be encouraged to follow this one. And then there are 2 more extensive data camp courses listed here, which of course you have access to if you're enrolled in our class. Now, these 2 data camp courses, they're not required courses currently. They're not assigned in our set of courses. But if you wish to delve deeper at this, or indeed at a later point, they're there for you at your beck and call, so to speak. Next up, we'll discuss some data visualization best practices. Basically, we're going to highlight how good visualization is optimized for the human visual system, what makes a good visual display of quantitative information. Always a good thing to keep in mind as we're going through our data analysis procedures. And before finally, for this unit, delving back into R proper to learn how we can make these sorts of informative and compelling and often just downright beautiful figures in R. So thanks for watching, and I'll see you then.